So thank you very much, Ivana, for the introduction. I have now the pleasure to introduce you to our SSG 2018 presentation. I'm Lukas Koppensteiner, I'm from Boco University, and yeah, let's get into it. So first of all, the general introduction. The thing is that crop production has many challenges to overcome in the future. For example, the increasing world population is putting quite a lot of stress on the crop production because the demands for crop production are rising. Estimated by 2050, global agricultural production will have to double to meet the future demands. Moreover, the climate projections predict changes in atmospheric CO2 level, in temperature and in rainfall pattern. And this will all have an effect on agriculture, of course. There are quite a lot of uncertainties involving the changing CO2 level, changing temperature level, on the effects on agriculture, of course. And in our SSG 2018 contributions, we talk about different topics concerning these challenges. So different students from different universities talk about different topics concerning these challenges. So I want to start with my part of the contribution of the SSG 2018 contribution on the topic of spectral measurements and selected vegetation indices in plant production and climate change. First of all, the objective. The objective is to discuss the aspects, benefits, the disadvantages, and the practical applicability of spectral measurements and, of course, vegetation indices in plant production and climate change research. But first of all, what are spectral measurements? So in the course of spectral measurements, the reflected radiation of a given plant canopy is detected. And this data is then used to calculate algorithms, so-called vegetation indices. And these vegetation indices can be used for numerous applications in general. So, for example, predicting different plant properties, or predicting yields, or detecting weeds and diseases. So, a bit more information on spectral measurements. In general, when light reaches an object, radiation is either absorbed, transmitted, or reflected, or a combination, of course. And as already mentioned, spectral measurements detect the reflected portion. Concerning the spectral characteristica of plant canopy, the challenge is that a lot of different factors, plant properties, influence the spectrum of reflectance of plants. But in general, one can say that concerning wavelengths below 700 nanometers, reflectance values are generally low. This is caused by chlorophyll, because chlorophyll absorbs a lot of light, especially in the visible range for photosynthesis. And in wavelength ranges above 700 nanometers, chlorophyll cannot use light at these wavelengths for photosynthesis. Here, especially important is biomass. So factors like the number of cells in plants or the cell structure is really important. Now onto the platforms for conducting spectral measurements. We differentiate between 3 different types, more or less. So we have satellites, we have aerial systems like drones, for example, and proximal systems. And of course, each individual platform has its own advantages, its own disadvantages. Let's start with satellites. So an important factor concerning satellites is the return frequency, of course. So this refers to the time between 2 consecutive measurements, spectral measurements of a given location. Concerning satellites, this is usually the time it needs to orbit the Earth once. Yeah, and also the spatial resolution is of course a big deal here, since satellites usually have a really high altitude. Therefore, the requirement for good spatial resolution is there. And cloudy conditions lead to some problems, because cloudy conditions, especially in combination with poor return frequencies, can lead to long periods of time without any useful spectral data of a given location. In general, satellite spectral data is especially useful for regional scale analysis of, for example, crop biomass and yields. Now onto the aerial systems. This is a kind of transition platform between proximal and satellite systems. Again, cloudy conditions can be problematic. The potential for aerial systems is, for example, agricultural management decision-making. So when the farmer goes to the field and wants to fertilize nitrogen or something like this, he can use a drone system for real-time and site-specific decision-making. And last but not least, proximal systems. These involve especially handheld devices or devices mounted on the tractor. And here I want to differentiate between active and passive spectrometers. So active spectrometers have their own light source. Passive spectrometers use the radiation from the sun, for example. And a quite interesting approach is the Onthego Monitoring, detection of plant properties. So some people maybe know the Yara N sensor, who is currently on the market already. It's a device where there are two light sources, active light sources mounted on a tractor with sensors for the reflected radiation. And when the tractor travels through the field, drives through the field, the N status of the plants is estimated, and at the back of the tractor there's the fertilizer sprayer mounted, and this information from the sensors in front of the tractor is then used for the application at the back of the tractor. So a quite interesting approach. Now on to some selected vegetation indices. The first is probably known by quite a few people, the NDVI. It's the Normalized Difference Vegetation Index. It's the reflectance ratio between infrared and red bands, and especially useful for leaf area index measurements and plant biomass. On the other hand, we have the NDRE, the Normalized Difference Red Edge, quite similar, but instead of the red bands, we use now the red edge bands. And the important thing for the NDRE is that it's quite sensitive for high levels of chlorophyll content. And finally, I want to mention the CCCI. This is a bit more specific, the Canopy Chlorophyll Content Index. It's calculated using NDVI and NDRE, and used to measure plant and nutrition. And this is also the vegetation index we use mostly for our current BOCO project on spectral measurements and vegetation indices. So our goal is to estimate the plant N status using CCCI in combination with another index, the CNI. So this is the Canopy Nitrogen Index. The Canopy Nitrogen Index is used to account for the N dilution effect. And this is all about the effect that plant N concentration during plant development usually decreases. So at the beginning of plant development, there's usually quite a high nitrogen plant concentration, and at later stages during development, this decreases. And the CNI is used to account for that, simply put, yeah. And we are working with many different crops. We work with wheat, maize, potato, and sugar beet. And we chose this approach, the CCCI-CNI approach, because it has been used in many different locations, and a lot of publications use it. And yeah, we'll see what the results will show. Now on to the combination spectral measurements with climate change research. A general goal is to estimate the typical responses of plants to various effects of climate change. One approach is, for example, to take historical weather data and combine it with information on plant characteristics based on spectral measurements. Another way of using spectral measurements to combat climate change is, for example, the improvement to resource use efficiency. So, as mentioned, site-specific N fertilization can lead to reduction in environmental impacts, for example, less N leaching and stuff like this. And finally, I want to mention the challenges, some of the challenges and opportunities of spectral measurements. First of all, 3 selected challenges. Of course, as mentioned at the beginning, there are a lot of factors that influence plant canopies, the spectra of plant canopies, and we need to find robust methods to estimate plant properties. And for example, also in our CCCI-CNI approach, we need a cultivar and site-specific calibration to use it. And moreover, the access to spectral data is quite problematic at the moment, since it's simply not available for some farmers or extremely expensive. And finally, some opportunities of spectral measurements. In general, farm management strategies can be optimized. This can lead to increases in farm profitability and less environmental pollution. And concerning climate change, as already mentioned, the climate change effects on crops can be estimated using spectral indices, vegetation indices. So, thank you very much. And now Anne-Marie is going to present her part of the presentation.